There's been a really interesting paper recently about the possibility that the Earth actually had two moons in its early phases of existence. So the way this would work is we currently believe that the moon itself was formed due to a Mars-sized body impacting the Earth and then throwing off a lot of debris into orbit. And over time, this debris slowly coalesces, comes together, and it can form in a variety of configurations. One is a single moon as we have now, but it's also possible that two moonlets, if you like, formed. And this is what the recent paper published in Nature describes. So the theory here is that you have a proto-lunar disk comprising this debris that was thrown off from the Earth, and that over time this condenses and it forms two objects. Now this has to be in quite a specific configuration so that they can actually survive for some tens of millions of years. But if it happens, what you can have is the primary, the larger moon, beginning to cool down, the magma oceans beginning to solidify, and then you can have this second smaller body also cooling down more quickly because it's a smaller body. So this can exist for some time in a very stable configuration, but eventually it's likely that there will be some perturbances that cause these two bodies to leave their stable positions. And what the authors of the paper hypothesize is that there could have been a rather slow, in planetary terms, impact. So these two bodies come together at just a few kilometers per second. Now this is still fast, this is still a few times the velocity of a rifle bullet, but it's slow in terms of planetary collisions. For very high-speed collisions, you often get craters formed, you get material thrown off from the surface, you can lose material from the body that you're impacting. In this case, what the numerical models that the authors produced show is that it may be possible for it more to splat. So you have an accretion, where material from this small moonlet ends up impacting and sticking almost to the moon. And one of the great things is that this could be an explanation for the big differences that we see between the lunar front side and the far side. And this is termed the lunar dichotomy, because on the near side, the side we see from the Earth, we see that it consists of rather low-lying, flat regions in which we term that the lunar maria, the seas. These are volcanically emplaced, they're rather smooth. These were the places that we know quite well from the Apollo missions and so on. Now the far side, that we know from observations by a spacecraft, this is quite different. The terrain is different, it's generally higher, it looks like an older terrain perhaps, or in some ways it's more cratered, it's rougher. It's quite a different texture from the front side that we see from Earth. So this new theory suggests that one explanation for this is that actually what we see on the far side is a result of this smaller moonlet impacting on the primary moon and effectively sticking there. So this has some interesting implications. Of course, it's hard to prove these theories. One possibility is that we could look at compositional differences, but in this case, because the theory suggests that both moons, the big one and the little one, accreted, that is, they came together from the same basic material. So in this case, it would be very difficult to determine any compositional differences between the two sides of the moon. Age is another possibility. We have techniques in the laboratory on Earth with which we can age rocks. However, the differences are relatively small. The small moonlet cooled first, and therefore it has an older surface in the way we measure lunar rocks. But we probably cannot measure this very easily, and certainly not with instrumentation in situ. However, there are still some instruments that we could emplace with missions like GLXP missions in order to tell us something more about the cause of this dichotomy. For example, seismometry is a very useful technique for determining the internal structure of the moon. And so this is where you basically have an instrument that couples to the surface, and you're listening for acoustic waves that basically flow through the surface and the subsurface of the moon. And then by looking at the attenuation and reflection of these waves, we can find something about where boundaries are between materials of different density, different compositions, say. So this is something that could quite easily be, for example, emplaced on the lunar surface, and several of these instruments could allow us to determine whether or not this theory is true and whether or not we really did have two moons in the night sky of the early Earth. One of the important questions about the moon is, what is the internal structure? Now, with any planetary body, this is one of the key questions. It tells us about how it evolved, what its composition is now, and really fundamental questions. And these are things that are very difficult to answer, even for the Earth, the planet we live on. For example, we can only dig holes to a very limited depth. We barely scratch the surface of the Earth. So we have to refer to techniques that are not so obvious. We have to infer from models and from techniques that probe the inner surface, but not directly. So one of these techniques that we use quite often on the Earth is seismometry. So this is when we have a sensor that is directly coupled to the surface of the body we're talking about, and then we detect either active or passive acoustics, basically. We listen for noises, for example, for earthquakes, for moonquakes in the case of the moon. We can potentially detect impacts on the surface. These are all sources of stimulation, if you like, of acoustic stimulation. And by studying the way that these sound waves flow through the surface and are transmitted and reflected by boundaries between different types of material and between, for example, the crust and the mantle in the moon, we can determine the depth of these regions. And by combining this with models, we can begin to build a picture of what the internal structure looks like. So every school child is very familiar with these for the Earth. You have a slice of pie showing you the iron core and then perhaps a molten region. But we have to remember that these, although these have been in our minds and textbooks for years, we still don't know these very precisely, even for the Earth. So it's important for the moon that we really try and get accurate measurements. And one way to do this, that can be done quite easily with, for example, a network of small missions, is to emplace seismometers onto the surface of the moon. And a network of these, 3, 4, as many as we can get, would enable us to really learn something about the deep structure. And so this is one method in which we can do this. An alternative method is that we can use retroreflectors. Now, these were left on the moon by the Apollo missions and also by the Lunar missions. These are basically small reflecting surfaces that are designed to very efficiently reflect light from the surface back in the direction in which it was sent. And what this means is that if you fire a laser beam from the Earth at a region that has one of these reflectors, you can determine accurately the distance between the reference station on the Earth and your reflector on the moon. And this is done quite regularly here on the Earth. In fact, here in Graz we have a station that does this regularly. Now, there are various things that we can tell from this. One thing is that we can try and measure subtle changes in the shape of the moon. The moon, for example, although we think of it as a solid body, it does undergo various tidal forces. It can be seen to expand and contract. And by measuring these very, very subtle, very small differences, we can again learn something about the internal structure of the moon. However, you have to be very careful when you make these measurements, because as we know, the moon is covered with a thick layer of basically soil, a very fine, very cohesive, ground-up material. And this responds a lot to sunlight that heats the surface. And so if you just place a seismometer or a laser reflector on the surface, one of the problems is that this can move during the day, during the night, as it gets hot and cold. And for these really sensitive measurements, we want both of these instruments, the laser reflector and the seismometer, to be really well in place, to be stuck to the surface so that what we measure is not variations due to night and day, but variations due to the large-scale dynamics of the lunar surface and of the lunar deep interior. So this would be a challenge, and a very interesting challenge, for a GLXP team wanting to emplace instruments of this type onto the surface. And we know that the Apollo astronauts, they had instruments that also they had to push into the soil, but it wasn't easy. The surface of the moon, the soil on the moon, the regolith, it sticks together, it's cohesive, the density of the soil increases quite quickly with depth, and there are some wonderful videos of Apollo astronauts really trying to push these instruments into the surface. So we know it's not easy. I mean, of course, you can take terrestrial techniques like drills and try and apply these to the surface of the moon, but there are various problems. You have to push this into the surface, your drill stem. You also have to remove the debris, and this is not as easy as it might seem on Earth. So recently, a few techniques have been developed that really take advantage of the vacuum environment that we have on the lunar surface. So one of these that's really promising is to use the idea of a suction drill. Now, the way this works is that you take with you some gas, and you create a drill as you would normally, but to remove the debris, you can flow gas onto and below the surface to the end of your bore, to the pointy bit of your drill, and then you can redirect that gas, and it uses the fact that the surface is at vacuum, and so the gas is accelerated upwards through your assembly, and it carries with it all the debris. So in this way you can really easily remove the debris, and you can imagine using this on a device that will actually push into the surface, removing the debris, blowing it out as you go, and creating the borehole that you can use to emplace your seismometer, your reflector, or other instruments. There are also other scientific instruments that really benefit from from being placed below the surface of the regolith to measure thermal conductivity, lunar heat flow, and other such measurements. So one of the things we have to consider about the lunar surface is that it has really cohesive materials. Now here we have something which is something like a lunar regolith sample. And on Earth, if we take some of this powder, it's very dry and it flows very easily. On the Moon this isn't the case, because the weight of the particles is much less, gravity is much lower, and therefore they tend to stick together, and the forces acting between particles tend to be much more dominant. So we have to bear this in mind. The way that our suction drill would work is if you imagine this pencil to be the drill itself, and that we flow gas through the pencil down to the drill stem here, and that we have around that a tube like this, then we would basically push this into the surface, and as we drill, gas would flow down through our drill to the drill bit, the bottom of our pencil here, and then the debris would be carried by the gas streaming back up towards the vacuum surface through our container here. And then the ejector, the material removed from the drill, is basically blown out here. But additionally, you could consider this as a way of getting material from the subsurface and transporting it to instruments in your lander or for sample return. So there are many uses for a device like this.